Okay, guys, I hope you're excited for our lesson today. It is an exciting lesson. Today, we're going to be dealing with the first fundamental theorem of calculus. It's going to bring together our stuff from the beginning of the year with our stuff this semester. It's going to connect indefinite integrals with integrals as area, definite integrals. It's going to really draw some things together. So get excited. Make sure you understand this well because this is a very important lesson. There will be numerous questions on the AP exam that come directly from this, and a lot of the stuff coming up later this semester will rely on this. So we've now studied two major branches of calculus. In the first semester, we studied derivatives. And the way we came up with derivatives, the way we introduced them, was we did limits. We did the limits of slopes. So we took, we said derivatives are the slope as you get closer and closer and closer together. We said if you took the slope of a nearby point and did the limit as those points got infinitely close together, that's the slope of the tangent line. And so the derivative tells us the rate of change of a function at a point. And this semester we've started with integrals. And integrals we introduced with limits of areas. Specifically, we did Riemann sums, but we said, look, if you've got a curve, you can estimate that, and if you do an infinite number of rectangles, if you make these rectangles get smaller and smaller and smaller, then you actually end up getting the exact area. So they both involve limits, but they don't seem particularly connected except that they can be used on curved lines. So here we go. Let's talk about something we should already kind of know, which is that if we have, this is velocity. If you do the integral of velocity, what does that represent? So the integral from 3 to 7 of v of t will represent what? Well, this area represents how far, it's like the end point of the car, end distance of the car minus the start distance. It's the displacement. We call this, I don't know if you guys have taken physics, but this is called displacement. It's where the car ended compared to where it started. Sometimes we'll say it's the distance the car traveled, although we have to be a little bit careful because if the car is going both negative distances and positive distances, velocities, then we need to be careful with our language. So sometimes we say how far the car traveled if everything's positive, but a lot of times we'll use the word displacement to just say it's the ending location minus the starting location. So how do we write this? Well, this is the ending location is the x, the position at t equals 7. So position at t equals 7 minus the position at t equals 3. So it's how far the car traveled if it's all positive, but it's really just like the ending position minus the starting position. And you might notice that I can rewrite this. Velocity is the derivative of position. So this is the same as saying the integral from 3 to 7 of the derivative of position, which is velocity, is equal to x of 7 minus x of 3. And so there's some relationship between integrals and derivatives, and that's what the fundamental theorem of calculus is going to tell us here. If we have a derivative function, okay, then the integral of that derivative function from a to b, this is like the area of the derivative function. So if you take the area of a derivative function, that will equal the original function. This is not f prime of x anymore. This is f of x. Its ending position minus its starting position. And this is like saying, hey, look, we take the area of those slopes. If we add up the area of those rates of change, it tells us how much a function changed by from beginning to end. Sometimes we'll write this as if we have a function and we do the integral of it, it will give us the antiderivative. So we'll use big F for the antiderivative. And it'll be the ending place of the antiderivative minus the beginning place of the antiderivative. This is, and it might not seem like much, but this is going to be incredibly powerful and let us do all sorts of things. There's even a nice way we can rearrange it. And I'll use this formula here. We can add the f of a to the other side to get, if you have a starting value of an antiderivative and you add in the integral of a function from a to b, this will equal what? Well, if we just added this to the other side, this is this plus this equals f of b. And this is a logical way to think about this is like the start plus the change equals the end. So again, remember the integral is an area. This integral from a to b is an area, but it's the area of like a rate of change and how much that finds the total amount something changed by. So if you start with something, add up how much it changed by, that'll tell you where it ends. So this is the change between a and b. And so let's look at how we're going to connect this to some things. First, we did this in a previous unit. We talked about how we could do this geometrically. Go ahead and find this integral, maybe using a graph on your own. What is the value of this integral? And hopefully we know this is the integral from x equals 1 to x equals 2. So it's between here and here of the function 2x plus 1. So looks like this. It's this integral right here. So this is a trapezoid with a height of 3 and a height of 5. The two bases are 3 and 5, so 3 plus 5 divided by 2 times 1. So, times 1. 3 plus 5 divided by 2. So this is 8 divided by 2 is 4. 4 times 1 is 4. This area is 4. But we have a new way we can do this. You don't have to do this geometrically anymore. What we can do is we can apply the fundamental theorem of calculus by thinking of this as the derivative of something, right? If this is f prime, then we can find the antiderivative. Let's find f. Or if you think of this as f, you can find, if this is f, then you can find the antiderivative f. So what is the antiderivative of 2x plus 1? So the antiderivative of 2x plus 1 is, we're going to raise the power by 1, divide by 2, so x squared, and then 2 divided by 2 is 1. We're going to raise the power by 1, so this is just x. So x squared plus x, the derivative of that is 2x plus 1 plus c, right? And what we're going to do is we're going to evaluate, the way we write this, you know how we said it was going to be this at the ending point minus this at the starting point? We'll write this like this. We'll write from 1 to 2. And what this means is you plug in 2, you plug in the ending point. So 2 squared plus 2 plus c, that's what happens when we plug in 2, minus, and I'm going to put this in parentheses because it all needs to be subtracted, 1 squared plus 1 plus c. And so 2 squared is 4 plus 2 plus c minus, this is 1 plus 1 is 2, so it's going to be minus 2 minus c. And we'll notice something. When we're doing this fundamental theorem of calculus, you'll always just get a plus c and a minus c. These will always cancel out. And so when we're doing definite integrals where it's from a to b, you actually don't need to put the plus c. Like, you don't have to put this because even though it is the antiderivative, it will always end up going away because you'll get a plus c and a minus c. Like when you plug in 2, you'll get something plus c. When you plug in 1, you'll get something plus c, and it'll always be c minus c, which will be 0. Okay, so these are the same thing, and what this is going to let us do is it's going to let us find the integral of curved lines. Let's look at this. Here's an indefinite integral, and in fact, this is very similar to one that we did when we were doing infinite Riemann sums. So here is x squared minus 1, and we are doing the integral from -1 to 3, and so it's like this area here. There's some negative area, there's some positive area, and we cannot find, I mean, we could do an infinite Riemann sum and like get infinitely close. Like we could do a whole bunch of rectangles here to estimate it, but we can't actually find this area without doing an infinite Riemann sum. But we can use the fundamental theorem of calculus to say, look, maybe we can think of this as a derivative. And so this integral is adding up all the rates of change of this slope. And so it's going to tell us how much if this is a derivative, then how much did f change by? And that's what this will represent. And so we're going to go the other way. We're going to find the antiderivative, see how much it changed by, and that's how much the area is going to be, and those will be equal to each other. So what is the antiderivative here? Well, hopefully we know we raised the power by 1, divided by 3, so 1/3, raise the power by 1, and we are going to evaluate the end, so this is the end, minus the start. So what is this at the end minus what was it at the start? That's how much it changed by, and that'll be this area. This area will be how much it changed by. So it's this from -1 to 3. That's how we write it. Go ahead and evaluate this. So we're going to plug in 3. So this is 1/3 of 27. 3 cubed is 27 minus 3. And I'm not going to put the plus c here. You notice I didn't put the plus c because when we do this minus part, it would have like a plus c and then a minus c, which goes away. So we don't have to put it. But if you did, it's okay. When we plug in -1, -1 cubed is -1/3. When we plug in minus -1, that's +1. And we'll need to subtract this. So this is 9 minus 3 plus 1/3. The minus distributes. Be careful about this minus. It always is going to need to distribute. It's going to be like a common error that people make. So please don't make it. 9 minus 3 is 6, minus 1 is 5, and 5 plus 1/3 is 5 1/3. So 5.3 repeating, or if we want to put it into thirds, that's 15/3 plus 1/3 is 16/3. So 16/3. All right, guys, again, these are ones that we could not find the area of, but we can do the antiderivative. Let's look back at this one. What this 5.33 represents is this is how much the antiderivative of this changed between -1 and 3. Right? And so that must be how much area this was. If we think of this as a rate, adding up all the rates has to give us 5.3333. So that's pretty cool. Try this one on your own. Try to do this one on your own. And hopefully what you started by doing was you did the fundamental theorem of calculus by finding the antiderivative. You could have put plus c or not. This is 2x to the 1/2 power plus 1. So when we raise the power, we're going to raise the power by 1. 1/2 plus 2/2. That's how we go up by 1 is 3/2. And then we need to divide by 3/2. So that's multiplying by 2/3. So 2 times 2/3. This is 2/1. That's 4/3. Plus x. And I'm not going to put the plus c. This is from 1 to 4. It's hard to evaluate 4 here. Let's rewrite this. This is 4/3 square root of whatever cubed. And I'm going to go ahead and plug in 4 here. So let's go ahead and plug in 4. We're plugging in the in value. Plus, we're going to plug in 4 here. Minus, in parentheses, make sure you're putting the parentheses here. It's going to be this value with 1 plugged in. So it's going to be 4/3 times whatever power we do 1 to, like square root of 1 is 1, 1 cubed is 1. This is going to be times 1 plus 1. Okay, so we're plugging in 1 into here. And we're plugging 4. So it's how much the antiderivative changed by from 1 to 4. Okay, square root of 4 is 2. 2 cubed is 8. 8 times 4/3, you just have to multiply times the numerator, is 32/3 plus 4 minus 4/3 minus 1. Make sure you distributed that minus to both. So let's see, this is 32/3 minus 4/3 is 28/3. 4 minus 1 is 3. And then 3 is 9/3. So 9/3 plus 28/3 is 37/3. So 37/3. Okay. And that must be what this area is. Wasn't that neat? Like, here, let's look at this in a calculator real quick. So here is y equals square root of 2. Oops, what did I just do? Square root, I think I put matrix. So 2 square root of x plus 1. And let's graph it from, this is fine. Let's go -5 to 5, -5 to 5. And here's this graph, right? Here's this square root function. And what we're saying is the integral, the area from 1 to 4, this area is 12.333, which is 37/3. That's what this area is. We found the area by doing the antiderivative and seeing how much that antiderivative changed by. It's neat. Okay, try this next one on your own. The integral from 0 to pi over 4 of secant squared. And hopefully you recognize, like, there's no way to do this without doing the fundamental theorem of calculus. You're not going to find this area. So the antiderivative of secant squared is tangent of x. We don't need to put the plus c because the c's will cancel out when we subtract the ending value from the starting value. Tangent of pi over 4. Okay, what is tangent? Tangent is sine of over cosine. So sine of pi over 4 over cosine of pi over 4. I don't actually know my tangent values. So, okay, so pi over, so here's pi over 2, pi over 4 is here, and so the sine and the cosine value will both be square root of 2 over 2. So this is tangent of pi over 4 minus tangent of 0, and tangent of pi over 4 is 1, because sine of pi over 4 is square root of 2 over 2, and cosine of pi over 4 is root 2 over 2, so it's the same thing divided by the same thing is 1. Tangent of 0 is sine of 0 over cosine of 0. Sine of 0 is 0, cosine of 0 is 1, so root 2 over 2. And so 1 minus 0 is 1. That's crazy. The integral of secant squared. Let's look at secant squared. Secant squared we have to put in as 1 over cosine. Oops. So 1 over cosine of x squared. Here's secant squared. That's how we type it into a calculator. And we're graphing it from 0 to pi over 4. So it's this weird, like, man, the calculator's having a hard time graphing it, right? So here it is. And we're doing the integral. Let's wait until it gets done. The integral, the area of this, oh man, what did I just do? The integral from 0 to pi over 4, and it's this area. That area comes out to be 1. Crazy. Okay, so that's an area of 1. Okay, nobody would have ever guessed that. This sometimes comes up as a table problem, and it says, okay, here we've got a function, we've got its derivative, and it wants to know what is the integral from -4 to -1 of f prime of x. And so go ahead and try this on your own. Hopefully you saw that what we need to do is use the fundamental theorem of calculus. The area of the derivative is the same as the function from the bottom to the end. So this is f of -1 minus f of -4. And we can just read that off of the table. F of -1 is -1.5 minus f of -4 is 0.75, so -2.25. Really easy problem if you know the fundamental theorem of calculus, that it's just like, oh, here's the area of a derivative, is just you do the antiderivative and plug in. Here's a calculator problem. You need a calculator for this. It says f is the antiderivative of this. So this must be f prime. It's saying this is f prime. F is the antiderivative of this, so this is f prime. Right. And f of 1 is 0, then f of 4 equals what? Well, hopefully we recognize that if they give us this is like a start point and they want the end, we can use that other form of the fundamental theorem of calculus where we take the start plus the change, and that will give us the end. It's the easiest way to do these, and these come up a lot. So this is going to be f of 1, so the start, plus the integral of f prime from, it has to go from the starting point to the ending point, will give us f of 4. Right, and this is, of course, rearranged way of saying the integral of 1 to 4 of f prime is f of 4 minus f of 1. So the starting value plus the integral is equal to f of 4. So we just need to plug in this integral, and the reason this is a calculator is like there's no way to do this antiderivative. You can't do this antiderivative. There's no quotient rule for integrals, and it's actually not possible to do this. What your calculator is going to do is it's going to make a bunch of rectangles and calculate the answer that way. Like that's what a calculator is doing. So it's going to do a whole bunch of rectangles and just round them. So let's look at what's going to happen here. So there is a button in our calculator. Let's learn about this. We know if we put it in, oh, hold on, I actually typed this into a different calculator so that I could quickly do this for you. We know that if we graph it, we can just do, like, there's an integral button. So here it is. Man, okay, this is annoying. Let's make it go from -1 to 5, -3 to 3. And we're going to make it go faster. Okay, so this answer, the integral, is this area. So it's the area. So you can press, so one way to do this is you put it into y equals. You can graph it, and then you can press second calc, and there's this integral button, and it'll ask you for the lower limit first. That's like, the lower limit means like from the bottom one. This is the lower limit. It's where it starts on the left. So from 1. Then it asks for the upper limit. The upper limit is 4. And here's this area. It tells us it is, oh man, it's taking it a while to calculate because it's doing a bunch of rectangles, is 0.376. So this is 0.376. Okay. Let me show you some other ways to do it. You can also, on the main screen, you can press, I'm going to write this down here. This is math. And then it's 9 is this is a definite integral. The int is int. It can also do derivatives at a point. So it can't find the derivative of a function, but it can do the derivative at a point. So the integral of, so f math 9, and then that'll get you the integral. And you're going to put in, it's going from 1 to 4 of, what's the function? X squared over 1 plus x to the 5th dx. You guys can't see that. Sorry. I was like moving it so I could see this, but then now you can't see it. So we're doing this integral. You always do it with x's, even if it's other variables, we'll do that. And that'll also come out to be 0.376. So same thing. Okay. One more way to do it is you can put the function into y1. This will become really helpful later when we get complicated functions and they like get mixed together. You can press integral, so math 9, just like before, math 9, that integral. And you still need to do from 1 to 4, but you can actually put in y, because we already put this into y1, right? So there's a way to get to that y1, and the way to get to it is you press variables, the variables button. So the variables button, and you go to y variables, and then you choose the function and you choose y1. This will be useful when we start doing complicated areas of things, and it'll also come out to be the same thing. So these are 3 ways to do it. Okay, and so remember we needed to add in f of 1. Now in this case, f of 1 was 0. That's not often the case. You'll see it actually in this problem and in another problem in this unit, but it's actually really important that you remember to add in the beginning plus the change is the end, and so there's our answer. Okay, but because it was 0, it didn't add in. If this had been like f of 1 was 3, it would be 3.376. Why don't you guys try this next one on your own? If g is an antiderivative of f of x, so if g is the antiderivative of this, then this is g prime, right? So g is the antiderivative. So g of 2 is -7. G of 4 would be what then? And hopefully you saw that this is, again, that same formulation where it's like the start plus, you're going to need to do the change, the start plus the integral from 2 to 4 of g prime, which is f, is going to equal g of 4, so the end. So it's the start plus the change is the end. And this is a really useful way to think about it a lot of times, and that's how it'll be here. So the start, -7, plus the change is equal to the end. Yep, good. All right, here's another one. Try this one on your own. You do need a calculator for this. So again, f is an antiderivative of this. That means that this must be f prime, right? This is the derivative of this one. If this is the antiderivative, this is the derivative. And so if f of 1 equals 0, I wish they weren't making it 0, but they did. This just came from an AP exam. So f of 1 equals 0, then f of 9 equals what? And hopefully you said, well, the way we're going to do it is we're going to add in f of 1, which will be 0, plus the integral from 1 to 9, the integral from 1 to 9 of the derivative, and that'll equal f of 9. So the integral from 1 to 9, you're doing this in a calculator, and I hope you were able to do it. I'm going to do it by pressing math 9, integral from 1 to 9, and the function that's the derivative of f of x is this one. And I'm going to press alpha y equals to get a fraction. This is natural log of x. I'm going to put it in parentheses. Natural log of x cubed. So natural log of x cubed over x dx. And so it's 0 plus... it actually takes the calculator a little while to do integrals, like it's not immediate, and it's because it has to actually make a bunch of rectangles. Like it can't do anything smart; it's just gonna make rectangles. Okay, this is a cool one. I want you guys to try this. I love this problem. I think this is a great problem. The graph of f is shown below. If the integral from 1 to 3 of f of x, so this is f, the integral from 1 to 3 of f of x is 2.3, and f prime of x equals f of x, okay, then f of 3 minus f of 0 is what? And I hope we recognize that, okay, so f of 3 minus f of 0 is going to be the integral of f prime of x from 0 to 3, right? This is like end minus start is going to be the change, which is going to be the sum of the rates. We're adding up all these rates. These are like, an integral is really a sum. I'll talk about that more later. And so that's, and f prime of x is f of x. So this, it's asking us for this area here, okay? But we have to put together our knowledge of a few different things. The integral from 1 to 3 of f of x is 2.3. So the integral from 1 to 3, this part is 2.3. Okay, now we just need to know the area of this part, because the area of this part plus the area of this part will be the area of the whole thing, which is what we're looking for. And this is a rectangle. So you can do this one using your geometry. 1 times 2 is 2. 2 plus 2.3 is 4.3. So we needed to, in this case, we needed to put together our limit properties to say like, hey, look, this is the integral from 0 to 3. So we're going to do the integral from 0 to 1 plus the integral from 1 to 3. It tells us the integral from 1 to 3. We can do the integral from 0 to 1 using our geometry. And we need to use the fundamental theorem of calculus to say that that area will be the antiderivative's change. Okay. Last one for the day. The tide removes sand at a rate. This is a rate. So this is like the, it's R of t, this rate is some sort of derivative of the sand. It's like amount of sand. It's the rate of change of the amount of sand. Whenever you see a rate is a derivative, right? So here is a rate. It's a derivative. In yards per hour, you can see that rate because it's per hour. How much sand will the tide remove from the beach during the first 6 hours? Indicate units of measure. So how do we find how much sand the tide will remove? Well, we've talked about this before. To find how much tide the sand removes, we need to do the integral of the rate. And it wants it in the first 6 hours. So this is t equals 0 to t equals 6. So from 0 to 6 of r of t dt. This is a calculator problem, by the way. And so what do we do? Well, guys, we will later this year actually learn how to find the antiderivative of this, but this is meant to be done using a calculator. It is just something you plug into your calculator. So we're going to do the antiderivative. So math 9 from 0 to 6 of 2 plus 5 sine of 4 pi. It says t, but we're going to put in x. You could do t, and then you just have to do t dt. But it's harder to get to, so it's easier to just change it all to x's, dx. Okay, here it is. This antiderivative, and it's going to take the calculator just a second to calculate it. It doesn't do it instantly. The amount of sand removed is 31.816. It's also fine to put 31.815. The AP exam allows 2 forms of rounding. It allows rounding by cutting it off, by just chopping off the end. And it also allows normal rounding, which is rounding up the next number to 6. And that's like, this is the normal way of rounding it, but you'd also get credit for putting 5. All right, guys, that is it for this lesson. Again, the big idea is that we now have a connection between areas, between integrals, between derivatives, all of these, and antiderivatives. They're all connected in that the integral of a derivative is how much that function changed by. So this is like the change is the sum of the rates. So if you add up all those rates, it tells you how much you changed by, and that should make some sense. Another way to rearrange that, of course, is if you know where you start and you know how much you change by, you can find where you end. So both of those come up these both come up, and you want to be very familiar with this. If you should be able to write it down without looking at anything and understand it. So let's try that right now. I hope you guys have a good rest of your day. If you have any questions, please ask. This is a really important unit, and it's really important that you learn this stuff very well. It's going to be coming up. Till the end of the year. It's not going away, and it's a big part of the AP exam as well. So, guys, do well with this. Ask questions if you're confused. It sometimes takes kids a little while to get used to this, but then it won't be bad.